its scheduled lifespan. That's the incredible reality of a bold NASA mission that is redefining space exploration. A mission that, despite the passage of time and the monumental challenges of operating in deep space, continues to push boundaries and astonish scientists and enthusiasts alike. This extraordinary voyage isn't just about reaching far-off places, it's about resilience, discovery, and the enduring human spirit of curiosity. But there's something even more fascinating. This brave spacecraft is not only miles, but millions and millions of miles from its launch point, and yet it continues to send invaluable data back to Earth. What's truly remarkable is that it does this using technology older than that of a cassette player. Imagine that for a moment. A machine launched in the late 1970s, armed with primitive computing and basic communication systems by today's standards, is still out there, relaying messages across the vast cosmic sea. And that's not all. The spacecraft, which was launched in 1977, just made a discovery so compelling, so profoundly mysterious, that it is shaking the scientific community to its core. It has captured the attention of the entire world, igniting both scientific debates and public imagination. What could this amazing find in the far reaches of space possibly be? And perhaps more intriguingly, what does it mean for us here on Earth? There was a key moment in history, an inflection point, when two of the most amazing space missions ever launched by humankind ushered in a brand new era of space exploration. These were not merely missions, they were odysseys, journeys into the unknown. This revolutionary turning point was made possible thanks to the brilliant and forward-thinking mind of Gary Flandreau, an engineer at NASA's Jet Propulsion Laboratory. His innovative thinking led to a historic breakthrough. With only a pencil, paper, and a 20th-century engineering mindset, Flandreau made a startling discovery. During the late 1970s and early 1980s, an extraordinarily rare and favorable planetary alignment was due to occur, an alignment of the four gas giants, Jupiter, Saturn, Uranus, and Neptune. They would position themselves in a unique cosmic configuration, like celestial beads strung on an invisible necklace, with Earth dangling at one end. This rare cosmic dance was no small matter. It would allow spacecraft traveling close to each planet to gain speed using each planet's gravitational pull, a technique known as gravity assist or gravitational slingshot. It's as if the spacecraft were being pulled along by an invisible rope, gaining velocity with every planetary pass. This brilliant maneuver could drastically cut down the travel time through the solar system. A journey from Earth to Neptune that would ordinarily have taken 30 years could be reduced to just 12 years. This wasn't just a clever trick, it was a once-in-a-lifetime opportunity, literally. This particular planetary alignment occurs only once every 176 years. Faced with such a fleeting and extraordinary chance, NASA knew it had to act fast. With incredible speed and precision, and only 15 days apart, they launched two identical spacecraft, Voyager 1 and Voyager 2, during the summer of 1977. Their mission? To take advantage of this rare cosmic window and explore the outer planets in a way that had never been done before. Little did NASA know at the time that these twin explorers would go on to break every conceivable record in the history of space missions. More than 45 years after their launch, both Voyager 1 and Voyager 2 are still operational, still sending back data, still going strong at the farthest edges of our solar system and beyond. These probes have become the farthest human-made objects in history, having traveled far beyond what was initially imagined, especially considering their original mission was only supposed to last 4 years. However, these interstellar pioneers were full of surprises. At the beginning of their journey, they delivered astonishing close-up images of Jupiter and Saturn's moons. These were not dull, inactive worlds as once believed. They were dynamic, complex, and teeming with activity. Some had volcanoes, while others had vast, frozen plains and mysterious atmospheric conditions. The discoveries forever changed our understanding of these distant corners of the solar system. Voyager 2, in particular, achieved historic milestones. It became the first spacecraft to approach Uranus in 1986 and Neptune in 1989. These encounters weren't just technical successes, they were landmark scientific events, providing humanity with our very first up-close look at these ice giants. Before that, they were little more than blurry orbs seen through telescopes. Voyager 2's journey turned speculation into knowledge, uncovering astonishing findings from territories that had remained completely unexplored. The spacecraft traveled more than 14 billion kilometers from Earth, boldly going where no probe had gone before. Despite their modest size, comparable to that of a Volkswagen Beetle, these probes defied expectations. They not only survived the harshness of deep space but continued to expand the boundaries of our knowledge. Their voyage began with a maneuver around Venus, leveraging its gravity, a feat never before attempted by any spacecraft en route to Mercury. This alone cemented their legacy as trailblazers. To reach Jupiter, the Voyagers traveled a distance more than 10 times the stretch from Earth to Mercury. And to do so, they had to pass through the treacherous asteroid belt, a region filled with debris and potential hazards. While Pioneer 10 and 11 had previously braved this celestial minefield, it was still an incredible achievement. The spacecraft had to rely on their onboard intelligence, all powered by computers with a mere 69 kilobytes of memory, a fraction of what even the simplest smartphone holds today. Data collected by instruments aboard each Voyager was stored on track tape recorders before being transmitted to Earth using a transmitter that operated on just 23 watts, about the same as a standard light bulb. These probes were equipped with 12-foot diameter satellite dishes to facilitate communication with Earth. Using radio waves that traveled at the speed of light, they continued to send and receive signals. But the ever-growing distance made this increasingly difficult. Each day, they moved 3 to 4 light-seconds farther from Earth. Over time, signals began taking more than 18 hours to reach us. An additional challenge was the increasing background noise generated by radio towers, televisions, cell phones, and other Earth-based sources. These noises began to interfere with the faint signals coming from the Voyagers, making it ever more difficult to hear their whispers from deep space. And yet, despite all these hurdles, the Voyagers endured. They kept transmitting data, unveiling unexpected phenomena in the interstellar void and consistently surprising scientists with new and puzzling discoveries. Their journey has done more than just provide incredible photographs or intriguing scientific data. It has fundamentally reshaped how we view the universe and our place within it. Beyond our own solar system lies a mysterious region known as the Oort cloud. This vast shell of comet-like objects is held together loosely by the Sun's gravity and extends all the way toward the nearest stars. Although the Voyager spacecraft are still making their way, slowly, towards this enigmatic boundary, they began their entry into true interstellar space when they crossed the heliopause. This is the outer boundary of the heliosphere, the vast bubble-like region of space dominated by the solar wind and magnetic field emanating from the Sun. Beyond it lies the interstellar medium, a different and largely unknown environment. Originally, the heliopause was estimated to be about 50 astronomical units, AU, from Earth, 1 AU being the average distance between the Earth and the Sun. As the spacecraft approached this threshold, it was decided to continue funding the mission, driven by the scientific potential of reaching and studying interstellar space. Yet crossing this boundary didn't go exactly as expected. Scientists anticipated that the transition would bring an abrupt increase in cosmic rays, high-energy particles traveling at near light speed, typically ejected by violent cosmic events like supernovae. But these rays are usually deflected by the heliosphere's magnetic field, which acts as a shield protecting our solar system from many external threats. As the Voyager probes moved deeper into this interstellar realm, scientists closely monitored any variations in the prevailing magnetic field. The interstellar magnetic field was expected to be oriented differently from the solar magnetic field. A change would indicate a crossing from the Sun's sphere of influence into a region influenced by other stars and galactic forces. However, something strange happened. The spacecraft didn't detect any significant change in the magnetic field as they crossed the expected boundary. It wasn't until August 25, 2012, that Voyager 1 finally confirmed its crossing of the heliopause. The data showed a noticeable increase in plasma density, one of the key signs scientists had been waiting for. But this confirmation came without the expected shift in magnetic field direction, leaving scientists puzzled. This was unexpected. It had been widely believed that as the spacecraft transitioned from a solar-dominated region to one shaped by other stars, there would be a detectable change in the magnetic field's orientation. Instead, the data hinted at a more gradual, mysterious, and complex boundary, one that may not be as clear-cut as previously assumed. And so, the Voyager mission continues, sending back clues and raising new questions. Every byte of data, every whisper from the darkness, teaches us more about the cosmic ocean in which our pale blue is just one drifting speck. It reminds us that space exploration is not just about rockets and distant planets, it's about unraveling the nature of existence itself. As the Voyager probes pressed farther into interstellar space, their continued survival defied all odds. Originally designed for a 4-year journey, they have now been operational for nearly 5 decades. This longevity isn't just an engineering miracle, it's a testament to the foresight and meticulous craftsmanship of the minds behind the mission. Every line of code, every panel, every sensor was created with precision, yet no one could have predicted their usefulness and reliability so far from Earth, and for so long. The spacecraft's power source, radioisotope thermoelectric generators, RTGs, convert heat released by the decay of plutonium-238 into electricity. When launched, these power sources provided each Voyager with roughly 470 watts of electricity. But over the years, the energy output has been slowly declining as the plutonium decays and the thermocouples age. Today, each probe generates less than half of its original power, around 200 watts. To conserve energy, NASA has been carefully shutting down non-essential systems, prioritizing instruments critical to gathering interstellar data. And yet, despite this strategic power down, the spacecraft continue to beam back data that is rewriting the textbooks of astrophysics. Their instruments still monitor cosmic rays, magnetic fields, and plasma waves. Even with just a handful of functional instruments, they are producing more valuable information per watt than any other mission in history. Communication remains one of the most impressive feats of the mission. Signals from the spacecraft are received by the Deep Space Network, an international array of giant radio antennas located in California, Spain, and Australia. These facilities track and communicate with interplanetary spacecraft as they journey across the solar system and beyond. Receiving a signal from Voyager is like trying to hear a whisper from over 20 billion kilometers away, using a phone line that was never designed to carry it. And the whispers they bring back are thrilling. One of the most intriguing discoveries made